YouTube. I'm going to do another notebook LM here, and this is about MUVERA, and it's about embedding engines can be very costly. For how many embeddings that need to be done and evaluated can be very, very costly with GPUs. So over the years, they've done different types of ways to try and reduce those vectors and try to increase the accuracy while reducing the GPU cost. I think the last one was PLAID. Yeah, the PLAID was pretty much the industry standard at one point, and it all came from there's different embedding models that are done over the years, and one of the main ones is ColBERT. That's kind of the big type of embedding that Google's using. So this comes from a release from Google Research, and so I put their PDF in here, their discussion in here, and their code base in here, and everything else. So this can cover it, and then of course the prompt that goes with it is so it can hopefully kind of decode it for people in our industry to understand what's going on here a little bit. So let me get this going. Oops. Get that? Yeah, there we go.
Welcome back to the deep dive. Our mission today is, well, to give you a shortcut right into some really cutting edge research that's happening like right now.
Yeah, stuff that's really shaping the tech foundations of modern search engines, recommendation systems, you name it.
Exactly. We're going deep into information retrieval, IR, and exploring that classic tension, the one that pretty much governs everything you find online.
The speed versus accuracy problem.
That's the one, the constant trade-off. How fast can you find something versus how good is the thing you find?
And it's a tension that's become, well, even more pronounced recently. Accuracy has jumped forward massively thanks to these complex deep learning models.
Right.
But those same models, they created a huge efficiency bottleneck. You might get super relevant answers, but if they take, say, half a second to show up.
Forget it. Useless at web scale.
Totally unusable. So today, we're going to crack open the architecture of a potential solution, something that aims to resolve this, maybe permanently.
Okay, let's unpack that. We're talking about this shift, right? From simple vectors to complex ones. For years, IR systems relied on embeddings, transforming data like your search query or a whole document into a single mathematical vector, the single vector approach, or SV.
Which was fast. That was the key advantage.
Fast, but maybe a bit limited. Lacked nuance.
Definitely. And that's where today's focus comes in. Our sources introduce a state-of-the-art algorithm designed to use the accurate, complex approach.
The multi-vector stuff.
Exactly. But crucially, with the speed of the simpler single-vector approach.
Okay, I'm intrigued. What's it called?
It's called MUVERA. That stands for Multi-Vector Retrieval Algorithm.
MUVERA. Got it. And the core idea we're chasing, the secret sauce here,
is MUVER's architectural trick. It's a concept called Fixed Dimensional Encodings, FDEs for short.
FDEs. Okay, so if you listening are involved in building systems needing fast contextual search, maybe e-commerce, internal knowledge bases, or even those RG systems for LLMs.
Retrieval augmented generation, yeah. Very relevant there.
Then understanding these FDEs is probably pretty essential.
Absolutely critical. And just to set the stage, to show how big a deal this is, let's hit them with the headline result.
Let's do it.
When they tested MUVERA against PLAID, PLAID was the previous best-in-class multi-vector system.
Okay.
MUVERA achieved, on average, 10% higher recall. So better accuracy.
Nice.
And wait for it, 90% lower latency.
Whoa. Okay, 90%.
90. NINETY.
That's not an incremental improvement. That's a different class of performance altogether.
It really is. It's the difference between a system groaning under load and one that just breezes through hundreds of millions of queries. A fundamental capacity change.
Okay, so let's dig in. Why did that massive bottleneck even exist before MUVERA came along?
Right, so as we touched on, information retrieval is basically finding the right stuff from a huge pile of stuff based on a query.
Simple concept, incredibly complex execution, like asking how tall is Mount Everest, or something more nuanced like best methods for deep sea mapping. And the system has to translate that natural language into something searchable.
Which is where those neural embeddings came in, decades ago now, really.
Yeah.
The single vector SV embedding approach was the breakthrough.
Taking every item, query, document, image maybe, and squishing it down into one single high-dimensional vector, a string of numbers representing the meaning.
All the meaning compressed. And this compression did something clever.
It made similarity geometric, right? If two vectors are close together in that high-dimensional space.
Their meanings are similar. The concepts they represent are related.
And because it's geometric, you can measure similarity with a simple math function.
The inner product, or dot product, as many people visualize it, super simple.
And that simplicity allows for really efficient retrieval algorithms, like maximum inner product search, MIPS.
MIPS is the unsung hero of fast search, honestly.
We mention it a lot, but maybe we should pause on it. MIPS is why current search is so quick, isn't it? It doesn't check every single document.
Exactly.
Yeah.
It avoids the brute force linear scan. MIPS algorithms are masters of geometric space partitioning. They build these clever index structures, trees, graphs, things like that, that carve up the embedding space. So when a new query vector comes in, the system instantly knows, okay, I only need to look in this small neighborhood.
Ignoring almost everything else.
Ignoring 99.9% of the data, potentially. That's where the speed comes from. And that's why SV models powered by MIPS were the standard for so long.
Okay, makes sense. So if SV models were so fast and efficient, why bother changing? Why introduce the complexity of multi-vector MV models?
Well, it comes back to that compression. Speed has a cost.
You lose detail.
You lose a lot of detail. Think about summarizing a whole book like Moby Dick in just one sentence.
You'd get the gist, guy hunts whale, but lose everything else.
Exactly. All the nuance, the symbolism, the descriptions, gone. SV embeddings suffer from that same kind of information loss. They capture the main topic, but miss the fine-grained details within a document.
Which leads us to the rise of MV models. Things like ColBERT started getting attention.
Right. These models said, forget the single vector constraint. Instead, they represent a data point, your query, your document, with a whole set of embeddings.
Not just one vector, but many. How many?
Often, it's one embedding for every significant token, or word, basically. So a document isn't one vector anymore. It might be 80 or 100 vectors.
Wow, okay. And the rationale behind that?
Contextual fidelity. Pure and simple. MV models capture much richer, more complex local relationships.
Local relationships, meaning?
Meaning the relationship between specific parts of the query and specific parts of the document. If your query is red apples for baking, and a document talks about cooking methods using Gala and Fuji varieties, the MV model can specifically match red to Gala and baking to cooking methods.
Ah, so it's matching word to word or concept to concept almost granularly.
Precisely. The document isn't just one blob of meaning. It's a collection of distinct, searchable ideas represented by those multiple vectors.
This allows for what they call late interaction, I think. The meaning isn't baked in up front.
That's a key concept. The individual token embeddings only interact or get compared during the scoring process itself, not beforehand. But, and this is a huge but, that late interaction, that granular comparison, demands a completely different way of measuring similarity.
Yeah.
You can't just use a simple dot product anymore.
Right. Which brings us to the crucial similarity metric for MV models. Chamfer similarity, sometimes called maxim.
And this is where the computational nightmare begins.
Okay, break down maxim for us. How does this chamfer thing actually work? It sounds complicated already.
It is. Compared to a dot product, imagine your query has, say, 30 token embeddings, 30 different vectors representing its meaning.
Okay.
Now take the first query embedding, maybe for the word recipe. The system has to compare that one query vector against all the document's embeddings. Let's say the document has 80 vectors.
So 80 comparisons just for the first query word.
Yes. It finds the single document vector, maybe for the word directions, that has the highest similarity score to recipe. It finds the maximum similarity for that query token.
And it keeps that score.
It keeps that maximum score. Then it throws away the other 79 comparisons for that query token.
Okay.
Then it repeats the entire process for the second query embedding. Compares it to all 80 document embeddings, finds the single best match, keeps that maximum score.
And it does this for all 30 query embeddings.
Every single one. Finds the best possible match within the document for each query part. Finally, after doing this 30 times,
Then what?
It sums up those 30 individual maximum similarity scores. That final sum is the overall chamfer score, the holistic measure of relevance.
Wow. Okay, I can see why that's accurate. It forces every part of the query to find a good home in the document. Nothing gets ignored.
Exactly. It ensures comprehensive relevance. But you can also immediately see the computational nightmare brewing.
Yeah, absolutely. Problem number one must be just the sheer volume of embeddings.
Increased embedding volume, precisely. Using something like ColBERT, a document that used to be one tidy 128-dimensional vector now explodes into, say, 80 or 100 vectors, each 128 dimensions.
That's like 80 times more vector data per document to store, index, and search through.
Orders of magnitude more data. It's huge.
And then problem two, the complex scoring, that process you just described.
It's not just one dot product. Chamfer matching involves finding that maximum for each query token, which is mathematically a nonlinear operation. It often requires a matrix product-like calculation. It's just fundamentally far more compute-intensive per comparison than a simple SV-ME paste calculation.
Which leads directly to problem three, lack of optimized algorithms. All those super fast ME pace algorithms we praised earlier.
They're useless here. Decades of optimization work poured into MIPAs, but it all relies on the geometric properties and linearity of the single vector dot product. They simply cannot handle the nonlinear sum of maximums nature of chamfer similarity.
So the tools that made SV fast couldn't be applied to MV.
Couldn't be applied directly, no. A standard MEPS index might get tricked. Imagine one query token finds a perfect match with one document token. A NICPS index might zoom in on that document, thinking it's highly relevant.
Even if the rest of the document is completely off topic for the other 29 query tokens.
Exactly. Because the MIPS index only sees that one strong local signal. It doesn't understand the holistic chamfer score. It can't rely on simple geometric neighborhoods anymore because the relevance is defined by this complex aggregation, not just a single point's location.
So the industry basically had to throw out the efficient MEPine playbook and invent workarounds, clunky alternatives.
Pretty much. Multi-stage pipelines, heuristics, complex systems designed to approximate MEFERCH without being able to use the truly optimized MIPI's tools. That's the efficiency gap MEVIA aims to close.
Right, so we've got this huge efficiency gap. MV models are accurate but slow, SV models are fast but less accurate, and the industry needed a bridge.
They needed something workable for web-scale systems, which led to the previous state-of-the-art approach before MUVERA. This relied heavily on what's called the single vector heuristic.
A heuristic, so like a rule of thumb, an educated guess, not a perfect solution.
Exactly. And the irony is, this heuristic desperately tried to shoehorn MIPS back into the picture, even though MIPS wasn't designed for MV similarity. It was a kludge, basically.
Okay, walk us through this heuristic. How did it try to fake MV retrieval using SV tools? It sounds doomed from the start.
It was a pretty convoluted multi-stage pipeline, often 4 stages in practice, like in the PLAID system. But the core flawed idea can be simplified. Stage 1 was brute force indexing.
What did they index?
They treated every single token embedding from every single document as an individual item.
Wait, so if you have 1 billion documents and each has, say, 80 tokens.
You create a MIP index containing 80 billion entries. Each entry is just one token's vector.
That index size alone sounds astronomical. Okay, what next?
Then your query comes in. Let's say it has 32 token embeddings. The system had to perform 32 separate MIPS queries against that giant 80 billion entry index.
32. One MIPS search for each query token.
Yep. Each search asking, find the document tokens most similar to this one query token.
That sounds incredibly inefficient. You're just hammering that massive index over and over again.
It's the opposite of elegant. And remember, each of those 32 MIPS searches returns the top matching tokens, not documents.
Right, because the index is built on tokens. So stage 2 must be figuring out which documents those tokens belong to.
Correct. Stage 2. Gather all the unique document IDs associated with the potentially tens or hundreds of thousands of tokens retrieved across those 32 searches. You have to deduplicate this list because one relevant document might have 15 tokens that popped up as relevant in those initial searches.
Okay, so now you have a big, messy, but deduplicated list of candidate documents, documents that might be relevant.
Might be. And only then, in stage 3, do you finally run the original, expensive, full chamfer similarity calculation, but only on this reduced list of candidate documents.
I see. So the first 2 stages are just a massive, inefficient filter to reduce the workload for the final accurate scoring.
Exactly. And this highlights the inherent flaws of the heuristic. First, running MIPS 32 times is just fundamentally slow and resource intensive.
Yeah.
Second, because each MIPS query only sees similarity at the token level, it inevitably pulls in a huge number of false positives.
Meaning?
Documents where maybe one token looked really similar to one query token, but the document as a whole is totally irrelevant when you calculate the full chamfer score.
So the initial MIPS stages are noisy.
Very noisy, which forces the system to retrieve a massive pool of candidates in stage 1 and 2, just to be sure it doesn't accidentally throw out the few true positives hidden in that noise. It has to over-retrieve.
It's forced to be overly conservative at the start, retrieving way too much stuff.
Which then makes the final, expensive chamfer re-ranking stage, stage 3, much slower than it ideally should be, because it still has too many candidates to process.
A vicious cycle of inefficiency.
Absolutely.
Yeah.
And this is precisely the problem that systems like PLAID were built to mitigate, not solve. PLAID was essentially the most optimized version of this flawed SV heuristic.
How did PLAID try to optimize it?
It introduced an even more complex 4-stage process. It had extra steps involving things like scoring based on centroids, vector decompression tricks, and multiple rounds of candidate pruning and filtering.
Wow.
All designed to try to chip away at that huge, noisy pool of initial candidates generated by the underlying SV heuristic before hitting the final chamfer re-rank.
Looking at the diagrams of PLAID in the source material, it doesn't look elegant. It looks like layers of fixes built on a shaky foundation, lots of conditional steps, thresholds, parameters.
And that complexity leads to fragility. That's a key point the sources make. Tuning PLAID wasn't easy. Reproducibility studies found it required significant effort and careful data-set-specific parameter tweaking to get optimal performance.
So if your data changed slightly,
Your carefully tuned PLAID pipeline could suddenly perform much worse. It lacked robustness.
okay, so we have an architecture, the SV heuristic, embodied by PLAID that's complex, fragile, hard to tune, and fundamentally inefficient. Let's really drive home how inefficient with that cost comparison from the source using the MS Marco data.
Right, this is where the numbers get really eye-opening. MS Marco is a standard web search benchmark. Documents average about 78.8 token embeddings each.
Okay.
When they analyzed the computational cost of just the initial search phase of the SV heuristic, those 32 MIPS queries,
Yeah.
they calculated the total number of floating point values being processed. For MS Marco, it's roughly proportional to $32 times 128 times 78.8 times, and dollars the number of documents, and 128 is the embedding dimension. A huge number.
Okay, but how does that compare?
They did a theoretical comparison, they asked. If we had a hypothetical single vector system, what dimension would its vectors need to have for a standard MIP search to involve the same amount of computation as that multi-stage SV heuristic?
Like an equivalent cost dimension. What was the number?
The equivalent single vector fixed dimensional encoding FDE dimension needed to match the computational cost of the SV heuristic was 322,764.
Whoa, hang on. 322,000 dimensions.
322,764. That's the effective computational burden the old heuristic was wrestling with.
That is absurdly large. That's the cost of trying to force a square peg, SVMAPS, into a round hole, MV chamfer similarity.
It was computationally grotesque, as the paper implies, and the vast majority of that computation was wasted on retrieving and processing candidates that would ultimately be thrown away as false positives.
Just to avoid missing the needles in the haystack.
Exactly. And as we'll see, MUVERA achieves better results using FDEs that are often under 10,000 dimensions. Maybe 20,000 at the high end. Orders of magnitude less.
Okay, the inefficiency is undeniable. So MUVERA wasn't about tweaking PLAID's 4 stages. It was about ripping out that whole flawed heuristic.
Complete replacement. Find an elegant way to reduce that 322,000 dimensional headache back down to something small enough for standard MIPs to handle efficiently.
Which brings us squarely to MUVERA, this elegant 2-step procedure designed to completely bypass all that complexity and waste we just talked about.
It's a fundamental rethink, really. The core concept is all about reduction, taking something complex and finding a simple, effective proxy for it.
And MUVERA's trick, its core innovation, is transforming that whole set of multi-vectors, the query set Q may be 32 vectors, and the document set P may be 80 vectors,
into just one single, relatively small, fixed-length vector for the query, let's call it very P, and one for the document, FDE. These are the fixed dimensional encodings, the FDEs.
Single vector in, single vector out. But the magic is how they're constructed, right? The MIPS proxy idea.
That's the absolute key. The goal is to construct vec and vecoron such that the incredibly simple inner product, Langle-vec, Wrangle, acts as a really good approximation of the complex nonlinear chamfer similarity score, vector and Berkeley.
So you replace the slow, complicated chamfer calculation with a fast, simple dot product between these proxy vectors, the FDEs.
Exactly. And that reduction is what unlocks the massive 90% latency improvement. Because if you can reliably approximate the true MV similarity with a simple linear dot product,
you can plug it straight back into all that highly optimized, off-the-shelf, single-vector MOS infrastructure. Stuff like Discan, Feskeys.
precisely, you get to leverage decades of optimization work on MOA solvers again.
You escape the heuristic nightmare.
Okay, but hold on. You said approximation. The inner product's Langlevec approximates the true chamfer score. It's not exact.
Correct. It's an approximation. Doesn't that mean there's a risk? Could this approximation cause you to miss the actual best document sometimes? The old heuristic was inefficient because it was trying so hard not to miss anything. Is MUVERA just trading some accuracy for speed?
That's the crucial question, and it's a fair one.
Yeah.
There is a trade-off inherent in using an approximation, but MUVERA's strength is that this trade-off is highly controlled and, importantly, comes with theoretical guarantees.
Okay, provable guarantees. What does that mean in practice?
It means MUVERA isn't just a heuristic that seems to work well. It's the first algorithm, according to the sources, that provides mathematical proof of the quality of its single vector proxy for chamfer similarity.
Proof about what specifically?
They prove that the FDE dot product provides an epsilon additive approximation to the true MV similarity.
Epsilon additive, meaning?
Meaning the difference between the proxy score
Yeah.
and the true score is guaranteed to be less than some small value, epsilon, with high probability. They can mathematically bound the error.
So they know how close the approximation is likely to be.
Yes. And by tuning the properties of the FDE, primarily its dimension, they can control that epsilon. They can make the approximation accurate enough that the probability of it causing a truly relevant document to rank outside the top K candidates, the ones you'll actually re-rank, becomes acceptably tiny.
So it's not a perfect filter, but it's a mathematically reliable enough filter for that crucial first stage. Much better than the old heuristics noisy approach.
Exactly. It replaces a fragile, complex heuristic that hoped to find the right candidates with a mathematically grounded, lightning-fast filter.
Which leads us to the beautifully simple MUVERA retrieval process. Just 2 stages, right? Compared to PLAID's 4.
So 2. Stage 1 is the fast MIPS-based filtering. First, you pre-compute the FTE vector for every document in your corpus.
Oh, wait.
Then you index all those document FDEs using a standard efficient MIPS solver like Discan. When a query $STU arrives, you compute its FDE.
Also quick.
Yeah, FDE generation is designed to be fast. Then you use that query FDE viccar to query the MIPS index. The index very quickly returns the top K document FDEs whose inner product with they get is highest. This gives you your initial candidate list of documents.
A small high probability list. Then stage 2.
Stage 2 is the quality refinement, chamfer re-ranking. You take that small list of candidate documents retrieved in stage 1, maybe just the top 80 or 100, and only then do you run the original exact, computationally expensive chamfer similarity calculation. Chamfer a P on them.
Got it. You use the fast FDE proxy to find a small set of likely winners, and then you use the slow, accurate method only on those likely winners to get the final precise ranking.
That's the core efficiency gain. You're running the heavy chamfer calculation on maybe 100 documents instead of needing the heuristic to sift through hundreds or thousands or trying to compare against billions directly. It's a streamlined, robust 2-stage process compared to the convoluted 4 stages of PLAID.
And there was one other theoretical advantage you mentioned earlier, that FDE generation is data oblivious. What does that mean again, and why is it important?
Right. Data oblivious means the way MEVR transforms the multivectors QP into the FDEs doesn't depend on the actual content or distribution of your specific document collection.
Unlike, say, K means clustering, which needs to see the data to find cluster centers.
Exactly. MUVR's transformation relies on randomized projections and partitioning of the embedding space itself, independent of where your particular documents happen to fall within that space.
And the benefit?
Robustness. It means the FDEs work well, even if your data distribution shifts over time, which happens constantly in real-world search. Your live query data might look different from the data you indexed initially. Because the FDEs are data oblivious, they remain effective. It also makes the system great for streaming applications where new documents are constantly being added without requiring a full retraining of the indexing structure. Tag 4. Deep dive into FDE mechanics.
Okay, we've got the what and the why. MUVERA reduces MV to SV using FDEs, enabling MIPs, giving speed and robustness. Now, the really intriguing part, How?
How do you actually do that reduction? How do you squash a set of 30 or 80 vectors down into one single vector in a way that magically preserves enough information to approximate that complex chamfer score?
Yeah, that sounds like the core trick.
It relies on a combination of geometry and probability, specifically randomized space partitioning.
Yeah, what's the intuition?
The basic idea is if two vectors are similar, close together in the original high-dimensional space, say R120K, they should be likely to end up in the same bucket or cluster after we partition the space. Dissimilar vectors should likely end up in different buckets.
So you carve up the 128-dimensional space.
You carve it up into all distinct regions or clusters. The FDE vector will then essentially encode information about which clusters the original multivectors landed in.
How do you do the carving, the partitioning?
They explored a couple of methods, but the preferred one, and the one that gives the data oblivious property, is SimHash. It's a type of locality-sensitive hashing, or LSH.
SimHash, how does that work?
Conceptually, SimHash works by drawing a bunch of random hyperplanes through the origin of the embedding space. Let's say you draw random hyperplanes.
Okay, just random dividing lines in high-dimensional space.
Exactly.
Yep.
These dicosim hyperplanes divide the entire space into B2 KSM unique regions. Each region is defined by which side of each hyperplane it falls on.
So every point in the space gets assigned to one of these $2K regions?
Yes. And the locality-sensitive part means that if two vectors are close together, high cosine similarity, they are much more likely to fall on the same side of most of those random hyperplanes and therefore land in the same region or bucket.
I see. So the bucket...
Okay, so wifey didn't understand what that meant. So imagine seeing a graph in 3D, right? So it's like a cube, okay? So data with certain scores gets mapped out in that in a 3D space, right? So imagine dots that are around inside this cube floating.
Like this.
Yes.
I understand.
Okay.
Based on connection to or
So
similarity.
all those scores of those documents are in that cube space, right? And how close they are to the query means they'll be the same spot area within the cube.
Okay, got it.
Okay.
So the closer they are closer together, the more chances they are the same.
The better match for the query.
Yeah.
But what they're talking about to reduce that time even further, then what they're doing is they're narrowing down where they're looking at in the 3D space. So it's like a cone.
So they're choosing they're choosing the parameters that it's guided by pushing it into a smaller space.
Well, they're excluding stuff that it may be probabilistically not important.
Okay.
So they use probabilistic there to
Probabilistic based on the content
Well,
previously searched or non-previously searched or whatever.
neither. It just has to do with the embedding scores. If it's too far away, probability says it's not a match.
Okay, got it.
So they're reducing the amount of work that they have to do.
Bucket ID itself becomes a proxy for similarity. Why SimHash over something maybe more intuitive like k-means clustering?
Good
I
question.
need more of
They
that.
did test k-means, but found it offered no real quality improvement. And, crucially, k-means is not data oblivious. K-means calculates his cluster centers based on the actual data points in your corpus.
Ah, so using k-means would break that robustness to data distribution shifts we talked about.
Exactly. SimHash keeps the partitioning purely geometric and random, independent of the specific documents, which maintains that crucial advantage.
Okay, space partitioned using SimHash. Now,
So you'll notice when people talk about clustering keywords, they have different ways they do that. K-means is one of those that's looking for centroid way to cluster things. They obviously have DB scan and a few other types of algorithms you can use for clustering content or keywords or entities, etc.
That makes sense.
the absolute core bit, the clever part, the asymmetrical encoding for query versus a document. You said the way they build the query FDE is different from the document FDE. Why?
This is critical. It has to be asymmetric because the target function they're approximating chamfer maxim is itself asymmetric. Remember how it worked?
Yeah, for each query vector, find the maximum similarity among all document vectors, then sum those maximums.
Right. Sum of maximums, the FDE dot product Langle needs to somehow mimic that specific sum of maximum structure.
If you just say averaged all the query vectors to get velos and averaged all the document vectors to get velar and took their dot product.
That would just give you a standard single vector representation of the query and document centroids.
And remember, with embeddings, there's multiple ways to look for similarities. You may have heard the term cosine similarity. So dot product is another type of similarity algorithm. And a third common one that Google uses is called Euclidean distance, if you want to look those up. No.
We already know that doesn't work
I'm
well.
gonna-
It loses too much information. That's the old SV approach.
So how does the asymmetry work? Let's start with the query encoding.
Okay. After partitioning the space into bullet clusters using SimHash, they construct the query FDE velar. This FDE is composed of bullet blocks, one block for each cluster dollars. The coordinate block for cluster dollars, let's call it velars, is calculated as the vector sum of all the original query vectors from query that happened to land in that specific cluster dollar.
And that's the average.
The sum.
Yeah.
If 3 query vectors fall into cluster dollars, you add them together to get velae. If no query vectors fall into cluster dollars, that block is 0. This summation process directly mirrors the sum of maximums in the chamfer score. Every query token's influence is added into the FDE.
Okay. The query FDE encodes the sum part. Now, how does the document FDE encode the maximum part?
This is where the asymmetry comes in. For the document encoding, they also construct babialar blocks, one for each cluster of areas. But the document coordinate block is not the sum. It's the centroid, or the average, of all the original document vectors from landed in cluster carriers.
The average. Why the average for the document?
Think about what happens in the dot product angle vehicle. It involves summing the products of corresponding blocks, like Lankel-Kurevec, across all clusters. If Perrier was also a sum, a document with many vectors in one cluster would get a massively inflated score contribution from that cluster, even if those vectors were only the best match for one query vector that landed there.
Right. Using the average centroid for the document block effectively normalizes the document's contribution from that cluster. It represents the average document vector in that region.
Exactly. So when the query sum block, representing the total query interest in that region, is multiplied by the document average block, representing the average document content in that region, the result mathematically approximates the maximum similarity part of the chamfer score for the query points landing in that cluster.
Wow. Okay, that is clever.
No.
Summing the query vectors and averaging the document vectors within each random partition, then taking...
The chamfer score is where they take some of the, it's like stage 3. This is where they do all the high-end processing. So they filter a bunch of the junk, and now they create embeddings of different documents and create an average of it.
Okay.
And then they, based on the average when it's done, they give you the one that matches the most.
The dot product of the resulting concatenated vectors that elegantly linearizes the nonlinear maxim function.
That's the heart of it. It reduces that complex matrix-like operation down to a simple inner product suitable for MIPS, all through randomized partitioning and this crucial asymmetrical encoding.
So the final FDEs are just formed by flattening and concatenating all these Ballard ordinate blocks.
Yes. And to improve the accuracy and stability of the approximation, they actually repeat the entire SimHash partitioning encoding process no reps times, using different random hyperplanes each time. The final FDE is the concatenation of the results from all repetitions.
Which makes the final dimension dFDE equals B times dPruge, where the dimension of the blocks usually same as original embedding dim, DD of SDE 102.81. So you can tune the final dimension by changing the number of initial partitions or repetitions.
Correct. More dimensions generally mean better approximation accuracy, but also larger vectors and slightly slower MIPS. It's a tunable trade-off.
Okay, that core mechanism is clear. Now, what about those advanced optimizations and practicalities? Real-world systems always have edge cases. What if a query vector lands in a cluster dollar, but no document vectors landed there?
Good point. If P is 0 because no document vectors from P0 fell into cluster dollars, then the contribution to the dot product for any query vector dollar landing in that cluster would also be 0.
Which might unfairly penalize the document, right? Maybe the document had a vector just outside the boundary of cluster dollars that was actually the best match?
Exactly. It could hurt recall unnecessarily due to the randomness of the partition. So they introduced a technique called filling empty clusters, specifically for the document FDEs.
How does it work?
If a document dollars has no vectors landing in cluster dollars, Instead of setting to 0, they set it to be equal to the single document vector from polars that is closest in the original embedding space to the conceptual center of that empty cluster dollars.
Ah, so it puts something representative in that empty document block, preventing an artificial zero score. A nice practical test.
It's a small fix, but helps maintain the quality of the approximation near partition boundaries.
And the other major optimization tackled the remaining bottleneck, that final stage 2 chamfer re-ranking, which could still be slow even on just 100 candidates. They called it ball carving or query clustering.
Right. Calculating the full chamfer score requires comparing each of the, say, 32 query vectors against all vectors in each candidate document. That's still a lot of comparisons, especially if you have 100 candidates.
But they realized the query vectors themselves might be redundant.
Exactly. In a query like best cheap red apples for baking pies, the vectors for best cheap red apples baking pies might be distinct. But in a longer phrase, or if words are very similar semantically, some of those 32 query vectors might be very close to each other in the embedding space.
So why do the expensive find maximum similarity step 32 times if some of those searches are basically duplicates?
Precisely. The idea is to pre-cluster the query vectors Q dollars before the re-ranking stage. They group query vectors that are very similar to each other, using a high similarity threshold of tau 37 to 7 cent, worked well experimentally, into clusters.
And then
For the final chamfer re-ranking, instead of using all 32 original query vectors Gowler, they use only the centroids of these query clusters. Let's call this smaller set QQ dollars.
So if 5 query vectors were very similar, you replace them with just one centroid vector for the re-ranking.
Essentially, yes. This significantly reduces the number of query points you need to run the expensive maximum calculation for in stage 2.
That's a really smart layered optimization. Fix the big indexing bottleneck with FDEs, then optimize the smaller re-ranking bottleneck by simplifying the query representation just for that stage.
And the results were significant. On the MS Marco dataset, this query clustering reduced the computational cost of the final re-ranking stage by a factor of 5.4 times.
Wow.
Yes.
With minimal impact on the final accuracy.
Apparently very little loss. It's a huge win for practical efficiency. Ruthless engineering.
Okay, the theory sounds solid. The engineering seems really clever with FDEs and query clustering. But does it actually work? Let's look at the experimental results. Did MUVERA deliver on that promise of replacing the monstrous 322,000 dimensional equivalent heuristic?
The evaluation setup they used was pretty thorough. They didn't just test it on one dataset. They used 6 diverse information retrieval benchmarks from the standard BIR collection.
BER, what kinds of tasks are in there?
It's a mix. You have classic large-scale web search like MS Marco, question-answering datasets like Hotpot QA and NQ, duplicate question detection like Quora, and even more specialized semantic search like scientific documents, SciDocs, and argumentation retrieval, Arguana.
So a good range to test robustness.
Definitely. It shows the method isn't just tuned for one specific type of query or document style. The underlying multi-vector embeddings came from cold TV2, a standard choice, with 2 128-1 dollars.
And the FDE dimensions they tested, were they small compared to that 322K number?
Oh, vastly smaller. They experimented with FDE dimensions ranging from around 1,000 up to 20,000. Still high dimensional, but orders of magnitude less than the effective cost of the old SV heuristic.
Okay, first test. How good are the FDEs just as proxies? The recall and candidate reduction quality, how well do they filter compared to the old way?
This is where the difference becomes stark. This metric basically asks, to achieve a certain level of recall, say finding 80% of the truly relevant documents, how many candidates do you need to retrieve in the first stage?
Fewer candidates is better, means less work for the expensive re-ranking stage. And this is where the old heuristic struggled, retrieving too much noise.
Exactly. The results showed FDEs are dramatically more effective as a filter. To get the same level of recall, MUVERA's FDEs consistently retrieve 2 to 5 times fewer candidates than the deduplicated output of the SE heuristic.
2 to 5 times fewer, that's already a big win.
But it gets better. If you compare FDEs to the raw, non-deduplicated output of the SV heuristic, which represents the actual initial load the old system had to process before deduplication,
Yeah.
FDEs retrieve 10 to 22.5 times fewer candidates.
And to 22 times fewer candidates pulled from the index. That's enormous.
It really highlights how much noise the old heuristic generated. Let's use that specific MS Marco example again to make it concrete.
Please do.
Okay, on MS Marco, to achieve 80% recall at up 1,000, meaning 80% of relevant docs are in the top 1,000 retrieved, MUVERA, using 4096 dimensional FDEs, needed to retrieve only 80 candidates in stage 1.
Just 80 documents passed to the rewinker.
Okay. The old SV heuristic, after deduplication, needed 300 candidates to achieve that same 80% recall.
300 versus 80, already much worse.
And the raw, non-deduplicated output of the SV heuristic for 80% recall was around 1,200 candidates.
1,200. Compared to MUVERA's 80, that's 15 times less efficient at filtering.
15 times more candidates need in downstream processing, including the expensive chamfer re-ranking on many of them. This comparison is probably the single clearest piece of evidence that the inefficiency wasn't inherent to MD models themselves.
It was the retrieval architecture built around them. The SV heuristic was the problem.
MUVERA fixed the architecture by creating a vastly superior proxy with FDEs.
Okay, so the proxy works brilliantly. Now for the bottom line, end-to-end latency and recall. Combining the FDE filter with the chamfer re-ranking, how did MUVERA stack up against PLAID overall?
The results were dominant, pretty much across the board, on nearly all the diverse BIR datasets.
Yeah.
MUVERA achieved, on average, that 10% higher recall we mentioned earlier, meaning more relevant results found and the 90% lower latency.
Better and faster. Significantly faster.
Up to 5.7 times faster in some specific configurations reported in the paper.
Right.
It just consistently outperformed the previous state-of-the-art.
And you mentioned robustness earlier. Was that borne out in the end-to-end tests? Did it need lots of tuning for each dataset?
That was another key finding. PLAID, being based on that complex multi-stage heuristic, needed careful dataset-specific tuning of its various pruning thresholds and parameters to perform well.
A pain for deployment.
A huge pain. MUVERA, in contrast, largely thanks to the data-oblivious nature of the FDE generation, showed remarkable robustness. They were able to use the exact same FDE configuration, funded
Yes.
in 240 dimensions, PQ, compressed, we'll get to PQ, across all 6 very different BIR datasets.
Same settings for web search, QA, argument mining.
Yep. And it achieved consistently high recall and low latency across all of them, with minimal to no dataset-specific tuning.
That's a massive practical advantage for anyone actually trying to deploy and maintain these systems. Less fiddling, more reliability.
Huge cost savings in terms of engineering time and operational stability.
Okay, faster, more accurate, more robust, easier to deploy. Sounds amazing. But what about the size? Even 10,000 dimensional FDEs sound large if you have billions of documents. Memory cost must be a factor.
Absolutely. For web-scale systems, the RAM needed to hold the index is often the single biggest cost driver. Storing billions of 10K or 20K dimensional floating point vectors is prohibitive. Which brings us to the final, crucial, practical piece, vector compression.
Can you compress these FDEs without destroying their delicate approximation quality?
Yes, they showed that FDEs are highly amenable to standard vector compression techniques, specifically product quantization, PQ.
PQ, can you give us the simple explanation? How does it shrink the vectors?
Think of it like creating a codebook for vector segments. Instead of storing the full precision floating point numbers for every dimension, you first break the large FDE vector, say 100 and 240 dimensions, into many small consecutive blocks, maybe blocks of 8 dimensions each.
Okay, so 1,280 blocks of 8 dimensions.
Exactly. Then, for each block position, you create a small dictionary or codebook of,
This is
say,
lava at the moment.
256 representative 8-dimensional vectors, centroids. These 256 centroids are learned from the data distribution. Each centroid gets an index number from 0 to 255, which fits in 1 byte.
Got it. A lookup table for 8-dimensional chunks.
Right. Now, when you want to store your actual running 240 dimensional FDE, you look at its first 8-dimensional block, find the closest centroid in the codebook for that block, and instead of storing the 8 floats, you just store the 1 byte index of that closest centroid.
And you repeat that for all 1,280 blocks.
Yep. So your original 1 to 240 floats get replaced by 1,280 bytes.
That's a massive reduction. What was the specific PQ setup they used?
They reported excellent results with PQ256-8. That means 256 centroids, fitting in 8 bits or 1 byte for blocks of 8 dimensions.
So 8 dimensions compressed down to 1 byte, that's a factor of. 8 dimensions 4 bytes float equal 32 bytes compressed to 1 byte. A 32x reduction in memory footprint.
Precisely. A 32-fold saving in RAM or disk space needed for the index. And critically, they found this had only a minimal impact on the final retrieval quality. Recall, the FDE approximation is robust enough to handle this subsequent compression noise.
That 32x saving is what makes MUVERA truly practical for massive scale, right? Takes it from academic possibility to deployable reality.
Absolutely essential. But here's something even more interesting. They found that using PQ compression actually improved the query speed.
Improved speed. Compressing data usually adds computational overhead for decompression. How did it get faster?
It seems counterintuitive, but it's all about memory bandwidth and cache efficiency, when the vectors are 32 times smaller.
You can fit way more of them into the CPU's fast cache memory.
Exactly. The MIPS algorithm spends much less time waiting to fetch vector data from slower main memory or disk. The computational cost of PQ distance calculations is low compared to the time saved by drastically reducing memory access.
So the bottleneck shifted from compute back to memory access, and PQ slashed the memory access needs.
That's the idea.
Wait, wait,
The
wait.
sources report that using PQ256.8 compression boosted the queries per second, QPS, by up to 20 times compared to using the uncompressed FDEs.
20
Wow.
times faster throughput because of compression. That's wild, makes it suitable for really high traffic environments.
Definitely pushes it into the realm of practical, high-throughput engines.
One last check. FDEs use randomization, SimHash. Does this randomness make the results unstable? If you build the index twice, do you get different recall?
They checked that specifically. They measured the variance in recall across multiple runs with different random seeds for the SimHash partitioning. The variance was negligible. The standard deviation in recall at 1,000 was extremely low, like 0.08% to 0.16%.
So it's incredibly stable. Despite the randomization, the law of large numbers kicks in with enough partitions and repetitions, giving a reliable result every time.
Exactly. It proves the method is robust and suitable for production systems where consistency matters. #tag outro.
Wow. Okay, this has been a really deep dive into the guts of modern search. Let's try and summarize the impact of MUVERA.
Well, fundamentally, it feels like it's solved, or at least dramatically mitigated, that core trade-off between accuracy and speed that has plagued information retrieval for years.
It lets us use the really rich, accurate, context-aware multi-vector models like ColBERT.
Without paying that crippling latency penalty we saw with the old heuristic-based systems like PLAID. The 90% latency reduction is the headline there.
And it does this by replacing those complex, fragile, four-stage heuristic pipelines
Which needed constant expert tuning.
with a much simpler, more robust, mathematically guaranteed two-stage approach.
So there you go. There's tonight's wonderful live stream and presentation.
New Wi-Fi?
No. Anyways, have a good night, YouTube.